telescope built to see the edge of existence is staring into the universe right now. And yet, most of what's out there remains unseen. James Webb is the most powerful space telescope ever created. Its mirror can capture light, so faint it began its journey billions of years ago. Light that crossed space before Earth existed, before the sun ignited, before atoms formed into anything familiar. And still, Webb can only see a fraction of what's real. This isn't a failure of engineering. It's a consequence of reality itself. Because the universe is not made of what we see. Roughly 5%, the remaining 95% doesn't shine, doesn't reflect, doesn't leave an image behind. It bends space. It shapes galaxies. It controls the expansion of the universe, but it never appears in a telescope image. This is where our intuition breaks. We assume that if something exists, it can be seen, that more powerful instruments reveal more truth, that with enough time and technology, nothing stays hidden. But the universe doesn't work that way. James Webb looks for light. It sees galaxies as they were billions of years ago. It sees the universe in reverse, frame by frame, traveling backward through time. Not a physical barrier, a fundamental limit. You shine a flashlight and see particles drifting nearby. The water itself, the thing holding everything together, remains invisible. No matter how bright the beam becomes, that's the universe we live in. Galaxies behave as if something unseen is holding them together. Without it, they would tear themselves apart. Space itself is expanding faster and faster, as if driven by an unknown force, not slowing down, accelerating. Scientists didn't invent these ideas to sound mysterious. They were forced to accept them because the math stopped working without them. The motions of galaxies didn't add up. The expansion of the universe didn't make sense. Gravity alone wasn't enough. So the universe revealed an uncomfortable truth. Most of what exists cannot be photographed, cannot be imaged, cannot be directly observed. James Webb doesn't show us everything. It shows us the boundary between what light can tell us and what lies beyond it. And that boundary is where the real mystery begins. Everything we know about the universe comes from one thing: not touch, not sound, not matter itself. Without light, the universe would be silent. When a star ignites, it announces its existence by releasing photons. When a galaxy forms, it paints its history into radiation. When matter moves, heats up, or collides, it leaves a trace in light. This is how we see, but this method comes with a price. Light is not instantaneous. It moves fast, unimaginably fast, but not infinitely so. At 300,000 kilometers per second, it still takes time to cross cosmic distances. That means looking farther into space is the same as looking further into the past. When James Webb observes a distant galaxy, it isn't seeing where that galaxy is now. It's seeing where it was billions of years ago. This turns the universe into a kind of time machine. Every image is a message delayed by distance, a signal that survived the journey. But here's the catch. Light only tells the story of things that interact with it. If an object emits light, reflects light, or absorbs light, we can detect it. If it doesn't, it might as well not exist to a telescope. No matter how advanced that telescope is, James Webb doesn't scan space itself. It doesn't map matter directly. It waits patiently for photons to arrive. And if no photons come, there is nothing to see. This creates a profound limitation. Most of the universe does not glow. It doesn't burn like stars. It doesn't shine like galaxies. It doesn't scatter light in any measurable way. Yet its influence is undeniable. Galaxies rotate faster than visible matter allows. Clusters remain bound when gravity shouldn't be strong enough. Light bends around invisible structures, revealing mass that cannot be seen. Astronomers didn't notice this because they wanted mystery. They noticed because the universe stopped obeying known laws. Something was missing. Not missing from space, missing from our ability to see. This is the moment where astronomy reaches its edge, where observation turns into inference, where seeing ends and reasoning begins. James Webb extends our vision farther than ever before. But it cannot change the rules of light itself. And those rules guarantee one thing. No matter how powerful our telescopes become, there will always be parts of the universe that remain unseen, because they were never meant to be seen by light at all. Here's the uncomfortable truth. Up, only a tiny fraction of reality. Not half, not even a quarter, less than 5%. When scientists say we can see the universe, what they really mean is this. We can see what interacts with light, but the universe does not owe us visibility. In the early 20th century, astronomers believed most of the universe was already mapped. Stars were counted, galaxies. The equations seemed complete. Then gravity broke the illusion. Galaxies were spinning too fast. So fast, by all known physics, they should have torn themselves apart. They didn't. Clusters of galaxies stayed bound when visible matter alone could not hold them together, be detected directly. Something massive was there, something invisible. This wasn't a small correction. It wasn't a missing decimal. It was a missing universe. Scientists gave it a name, not because they understood it, but because they didn't. Dark matter. Not dark as in evil. Dark as in unseen. It doesn't emit light. It doesn't reflect light. It passes straight through telescopes, as if they aren't even there. James Webb cannot see it. Hubble cannot see it. No optical instrument ever will. And yet, without dark matter, galaxies wouldn't exist. Stars wouldn't form. Structure itself would collapse. Dark matter acts like scaffolding, an invisible framework holding the cosmos together. But that's only part of the problem, because even if dark matter accounts for missing mass, it doesn't explain expansion. In 1998, astronomers made a discovery that stunned physics. The universe isn't slowing down, it's accelerating. Galaxies aren't just moving away from each other. They're being pushed apart by something unknown, something that works against gravity, something that fills all of space. They called it dark energy. Again, not because they understood it, but because they didn't. Dark energy doesn't clump. It doesn't form objects. It doesn't shine. It simply exists everywhere, and it dominates everything. When scientists added up the universe, the result was shocking. Approximately 5% normal matter, approximately 27% dark matter, approximately 68% dark energy. That means 95% of reality is fundamentally invisible, not hidden behind dust, not too far away, invisible by nature. James Webb can see farther back in time than any telescope ever built, but it is still blind to most of what controls the universe. We are observing the shadows on the wall, not the structure casting them, and the deeper Webb looks, the clearer that limitation becomes. James Webb is the most powerful space telescope ever built. Its mirrors are larger than a house. Its instruments are more sensitive than anything humanity has ever launched. It can detect heat from objects billions of light years away. And yet, there is a hard limit it cannot cross. Not because of technology, not because of funding, not because we haven't tried hard enough, because of physics. James Webb is still a telescope, and telescopes only see one thing. Even infrared Webb's specialty is still light, just stretched, just shifted, just delayed. Dark matter does not emit light. Dark energy does not emit light. They do not glow, scatter, reflect, or absorb photons in any detectable way. No mirror can collect what was never sent. Imagine trying to photograph the wind. You can see its effects. Trees bending, dust moving, but the wind itself never appears in the image. That's exactly how dark matter works. James Webb sees galaxies rotating too fast. It sees clusters held together by invisible mass. It sees light bending around empty space. But the source of those effects remains absent from the picture. Webb doesn't reveal dark matter. It reveals where dark matter must be. And dark energy is even worse. Dark energy doesn't form structures. It doesn't clump into regions you can point at. It doesn't sit anywhere specific. It's everywhere, evenly. There is nothing to image, no boundary, no shape, no signal. The only way we know dark energy exists is by watching the universe misbehave. Distances grow faster than gravity allows. Expansion accelerates when it should slow. James Webb can measure that expansion with extreme precision. But measuring is not seeing. This is where many people misunderstand the telescope. Webb is not designed to reveal everything. It's designed to reveal early light, the first stars, the first galaxies, the first moments when darkness began to break. Ironically, the deeper Webb looks into the past, the more obvious the invisible becomes. Early galaxies appear too massive, too organized, too mature, as if something unseen helped them form faster than physics predicts. James Webb didn't fail. It succeeded so well that it exposed how incomplete our picture truly is. We built the ultimate eye and discovered the universe is mostly blind to eyes. If we can't see it, how do we know it's there? This question haunted astronomers for decades. Science doesn't work on belief. It works on consequences. You don't need to see a black hole to know it exists. You see stars orbiting nothing. You see matter heating, stretching, tearing apart. Dark matter and dark energy were discovered the same way, through what they do, not what they show. In the 1930s, astronomer Fritz Zwicky studied a cluster of galaxies called Coma. He measured how fast the galaxies were moving. They were moving too fast. According to visible matter alone, the cluster should have flown apart long ago, but it didn't. Zwicky called the missing mass Dunkelmatter, dark matter. For decades, the idea was controversial. Many thought gravity itself was wrong. Then evidence stacked up. In the 1970s, Vera Rubin measured how stars orbit within galaxies. Stars far from galactic centers were moving just as fast as stars near the core. That shouldn't happen unless something invisible was adding gravity. Again and again, the same pattern appeared. Galaxies, clusters, large-scale structures, different locations, same impossible math. The most striking proof came from gravitational lensing. When light passes near massive objects, space itself bends. This causes background galaxies to stretch, distort, and duplicate. Sometimes this bending occurs where there is almost no visible matter at all. The lens is there, the mass is there, but the light source isn't. That invisible mass maps perfectly with where dark matter is predicted to be. Dark energy is confirmed differently, by distance. In the late 1990s, astronomers studied exploding stars called Type Ia supernova. These explosions have a known brightness. By comparing how bright they appear, scientists can calculate distance. What they found was shocking. Distant supernovae were farther away than expected. The universe wasn't slowing down. It was speeding up. Something was overpowering gravity on cosmic scales. No telescope ever saw dark energy, but every precise measurement points to its influence. Cosmic microwave background radiation, large-scale galaxy surveys, expansion rate measurements, all independent, all consistent. Science doesn't require visibility. It requires consistency. And the invisible passes every test. We don't think the universe is 95% unseen. The math demands it. Remove dark matter, galaxies fall apart. Remove dark energy, the expansion history breaks. This isn't mystery for mystery's sake. It's a universe revealing itself through consequence. And that leads to a disturbing realization. Everything, familiar, stars, planets, life, is built on top of something we cannot directly observe. The visible universe is the exception, not the rule. When we talk about the size of the universe, most people imagine a giant bubble, a vast but finite space, filled with galaxies, ending somewhere beyond what we can see. That image is wrong. What we usually call the universe is actually something much smaller. It's called the observable universe. This is not the universe as it is. It's the universe as light allows us to see it. The observable universe is defined by a simple rule. Light must have had enough time to reach us since the beginning of cosmic expansion. The universe is about 13.8 billion years old, so you might expect the observable universe to be 13.8 billion light-years across. But it isn't, because space itself expands. While light travels, the universe stretches beneath it. Distances grow, while photons are in transit. In fact, the observable universe is about 93 billion light-years across. That number alone is difficult to grasp. But here's what makes it unsettling. That's not the size of the universe. That's just the part whose light had time to reach us. Beyond that boundary, space continues. Galaxies exist, whose light will never arrive here. Not because they're hidden, but because the universe expands faster than their photons can travel. They are permanently disconnected. Not over time, forever. Even worse, the observable universe is shrinking. Not in size, but in access. They vanish, not by destruction, by isolation. James Webb extends our reach deeper into cosmic history, but it cannot break this boundary. No telescope ever will, because this limit isn't technological. It's built into space-time itself. This means something profound. No matter how advanced our science becomes, no matter how long civilization survives, there will always be regions of the universe we can never observe. Not now, not later, not ever. We are surrounded by an unknowable ocean of space, and we are trapped inside a tiny, fading window. Everything we call reality, every law of physics we've discovered, is based on this limited sample. We don't study the universe, we study our visible island within it. And that raises a terrifying question. What if our island isn't representative at all? The boundary of the observable universe feels like an edge, but it isn't. There is no wall, no barrier, no ending, just a limit to what light can tell us. Beyond that horizon, the universe does not suddenly stop existing. Space continues, governed by the same expansion that hides it from us. According to modern cosmology, there is no reason to believe the universe ends just beyond what we can see. In fact, the opposite is more likely. Many models suggest the universe is vastly larger, possibly infinite. If that's true, then our observable universe is a tiny bubble in an endless expanse, a single frame from an unending film. And if the universe is that large, something unsettling follows. Everything that can happen, it'll happen, given enough space. Every possible arrangement of matter repeats. Stars, planets, galaxies, even histories. Somewhere unimaginably far away, there may be a galaxy identical to the Milky Way, a star identical to the Sun, the planet identical to Earth, and on it, a version of you. Not metaphorically, physically. This isn't science fiction. It's a mathematical consequence of infinite space and finite particle arrangements. But even if the universe isn't infinite, it may still be far larger than we imagine. Cosmic inflation, a rapid expansion in the universe's earliest moments, could have stretched space far beyond our observable region, like seeing a single square centimeter of an ocean and trying to understand the entire sea. This means our measurements of physics may be incomplete. They might only apply here. Elsewhere, physics itself could be different. Different stars, different chemistry, different rules. Our universe may not even be unique. Some theories suggest it is just one bubble among many, a multiverse. Each bubble expanding, cooling, forming its own laws. Most of them forever disconnected from ours, unobservable, unreachable, untestable. James Webb will never see these realms. No telescope will, because this isn't about distance. It's about cosmic causality. Some regions of reality will never influence us, and we will never influence them. They might as well be different universes entirely, which leads to the most humbling conclusion of all. Everything humanity has ever seen, everything we have ever measured, everything we call the universe, may be a tiny, biased sample of something far larger. We are not at the center. We are not special. We are observers, trapped inside a cosmic horizon, trying to understand an ocean by studying a single drop. At this point, a question naturally emerges. If we can only see 5% of reality, if most of the universe is forever hidden, if even our observable region is shrinking, then what is science actually doing? Is astronomy just guessing in the dark? The answer is no, but it is more humbling than most people expect. Science is not the pursuit of total knowledge. It never was. It is the pursuit of reliable knowledge within limits. Every scientific theory is a map, not the territory. A simplified model that works where it's been tested. And remarkably, even with such limited access, those maps work astonishingly well. We predicted black holes decades before we could observe them. We calculated gravitational waves a century before detecting them. We inferred dark matter without ever seeing it directly. Not by imagination, but by consistency. The universe obeys patterns, and those patterns persist, even when parts of the system are hidden. That's why James Webb matters so much. not because it reveals everything, but because it sharpens the edges of what we don't know. Every time Webb looks deeper, it tests our assumptions. Early galaxies appear too massive, too structured, too evolved, which tells us something is missing from our models. And that's how science advances, not by confirming comfort, but by exposing contradiction. Limits are not failures. They are information. The cosmic horizon isn't a wall telling us to stop. It's a boundary telling us where our theories must change. Even the fact that 95% of the universe is invisible is not a defeat. It's a discovery, a reminder that reality is richer than perception. Humanity once believed Earth was the center of everything. Then we learned we orbit the sun. Then we learned the sun is one star among billions. Now, we've learned that even matter itself is a minority. Each step reduced our importance and expanded our understanding. Science doesn't promise certainty. It promises progress. And progress doesn't require omniscience. It requires curiosity, the willingness to say, we don't see it, but its effects demand explanation. That mindset took us from cave fires to space telescopes, and it's the same mindset that will carry us forward, even if the universe keeps most of its secrets. James Webb did not rewrite the universe. It did something more unsettling. It showed us how early we were wrong. For decades, cosmology followed a clean narrative. First darkness, then simple stars, small galaxies, slowly complexity. James Webb shattered that timeline. The earliest galaxies aren't fragile. They aren't dim, aren't chaotic. They are massive, organized, rich in stars. Some host black holes, billions of times more massive than expected, at a time when the universe was barely old enough to form them. This shouldn't be possible. There wasn't enough time, not enough matter, not enough structure. And yet there they are. James Webb didn't just extend our vision, it exposed cracks in our understanding, cracks that widen the deeper we look. The telescope confirmed something profound. The universe didn't grow slowly into complexity. It exploded into it. Structure formed faster than our models predict. Order emerged where chaos should have ruled, which means one of three things must be true. Either our understanding of gravity is incomplete, dark matter behaves differently in the early universe, or something fundamental about cosmic evolution is missing. None of these options are comfortable. All of them are revolutionary. James Webb also proved something else. The universe does not care about our expectations. It doesn't follow narratives that feel intuitive. It doesn't evolve at a pace we find reasonable. It simply obeys deeper rules, rules we are still uncovering. And that brings us back to the original question. Why can we only see 5% of the universe? Because visibility was never guaranteed. Flight is a local messenger. Reality is not obligated to announce itself. James Webb is not a window to everything. It's a spotlight, revealing how much remains in shadow. And that shadow isn't empty. It's active, influential, dominant. The visible universe is not the foundation of reality. It's the surface, a thin layer floating on top of something vast and unseen. James Webb didn't give us answers. It gave us better questions. And in science, that's the real breakthrough. What if the problem isn't what we can't see, but how we think? For centuries, physics assumed something simple. What we observe is representative of reality. Stars behave a certain way. Matter clumps. Gravity pulls inward, so we built our laws around what was visible. But what if visibility itself is the bias? 95% of the universe does not interact with light. That means nearly all of our theories are built on a minority sample. Imagine trying to understand the ocean by only studying foam on the surface. That's essentially what cosmology has been doing. Dark matter and dark energy weren't predicted by theory. They were discovered because theory failed. Galaxies shouldn't rotate the way they do. The universe shouldn't expand the way it does. Instead of rewriting everything, we added placeholders. Dark matter, dark energy, not explanations, labels. This raises an uncomfortable possibility. What if gravity behaves differently on large scales? What if space-time itself has properties we don't yet understand? What if our equations work locally but fail globally? Some physicists think dark matter may not exist as a particle at all. Others suspect gravity changes over cosmic distances. Some propose entirely new frameworks. None of these ideas are fringe anymore. They exist because the data demands alternatives. James Webb intensified this tension. Early galaxies are too massive, too evolved, too structured. As if the universe skipped steps, as if something accelerated formation in ways we don't yet grasp. The deeper we look, the more the universe refuses to follow our expectations, which suggests a radical idea. We may not be missing pieces of the universe. We may be missing the correct way to think about it. Physics rests on a bold assumption that the laws of nature are the same everywhere. Same gravity, same constants, same rules. But what if that's only true here? Our observable universe is one region, one patch of space-time. We assume it represents the whole, but we've never tested physics beyond it. Cosmic inflation suggests our region may be unusually smooth, unusually stable, unusually tuned. In other regions, conditions could differ. Gravity might be stronger. Particles might behave differently. Chemistry itself might fail. This idea terrifies physicists because it means there may be no single theory of everything, only theory of here. James Webb can't test this directly, but it hints at it. The early universe looks too ordered, too efficient, almost as if our cosmic neighborhood formed under special conditions. If that's true, then dark energy might not be a force at all. It could be a property of space-time unique to our region. Dark matter might not be matter. It might be geometry. We don't know yet, but the cracks are real. From cracks are where revolutions begin. There is a comforting illusion in science, the idea that the universe is ultimately understandable, that with enough time, enough data, enough intelligence, everything will make sense. But the deeper we look, the more that promise begins to fade. 95% of reality is invisible, not hidden behind distance, not obscured by dust, invisible by nature. That alone forces an uncomfortable question. What if there are limits? Not to technology, but to understanding itself. Human cognition evolved to survive on a small planet, around a single star, in a narrow band of reality. We are not built to intuit cosmic scales. We are not designed to grasp infinite systems. Yet we try, and most of the time, remarkably, we succeed. But sometimes the universe pushes back. Dark energy accelerates expansion for no known reason. Dark matter shapes galaxies without revealing its nature. Early cosmic structures form faster than logic allows. These are not small gaps. They are foundational. And if our models are fundamentally incomplete, then predictions become fragile. Navigation through the future of the universe depends on assumptions we may not fully understand. This isn't just philosophy. It affects how we interpret cosmic fate. Will expansion continue forever? Will space tear itself apart? Will dark energy change over time? We don't know. And that uncertainty matters, because civilizations plan based on stability. Science builds on expectation. Meaning itself often relies on the belief that the universe is coherent. But what if coherence is local? What if order is the exception and chaos is the rule? That doesn't mean the universe is hostile, but it may be indifferent to comprehension. And that idea unsettles us, because it places a ceiling on certainty. But there is another way to see this. Limits are not always walls. Sometimes they are invitations. Every time humanity encountered a boundary, it didn't stop. It redefined the problem. We couldn't see microbes, so we invented microscopes. We couldn't feel radiation, so we built detectors. We couldn't observe space-time, so we listened for gravitational waves. The invisible has always resisted us, and we have always adapted. Dark matter and dark energy may seem unreachable now, but so did atoms. So did black holes. Already, scientists are designing experiments that don't rely on light at all. Precision measurements of gravity, maps of space-time distortion, quantum sensors, sensitive to the faintest anomalies. We are learning to listen to the universe instead of just looking at it. And there's something deeply human in that. We exist in a reality that does not reveal itself easily, and we still choose to understand it. The fact that most of the universe is invisible doesn't diminish us. It elevates the act of discovery. It means knowledge is earned, not given. And perhaps the greatest opportunity lies here. If we ever understand what the universe is truly made of, we won't just change cosmology, we'll change how we see ourselves. Because we will have learned how to think beyond perception, beyond intuition, beyond what evolution prepared us for. And that is how civilizations grow up. Before we continue, a brief note. If this video makes you think, if questions about the universe genuinely interest you, liking the video, subscribing, and sharing your thoughts in the comments helps this content reach others who are just as curious. Thank you for supporting long-form science. Now, let's continue. In a universe where 95% of reality is invisible, the existence of conscious observers feels almost absurd. Atoms drifted through space for billions of years. Stars ignited and died. Galaxies collided and reshaped themselves. And from all that chaos, something began to ask questions us. Humanity is made from the most ordinary material imaginable. Hydrogen, carbon, oxygen. Nothing exotic, nothing rare, yet arranged in a way that allows the universe to look back at itself. This creates a deep tension. On one hand, we are insignificant, a species on a small planet, orbiting an average star in one galaxy among hundreds of billions. On the other hand, we are the only place, as far as we know, where the universe becomes aware of its own existence. That awareness didn't come easily. The cosmos did not evolve for us. It did not prepare explanations. It did not simplify itself for comprehension. We had to earn every insight. Every equation was extracted from confusion. Every discovery came from contradiction. And now we face the biggest contradiction of all. Most of reality cannot be seen. Not because we are primitive, but because perception itself is limited. This forces a humbling realization. Human intelligence may not be the final interpreter of the universe, just one layer. We understand patterns, we build models, but reality may operate on levels that never fully translate into intuition or language. That doesn't make our search meaningless. It makes it extraordinary. Because, despite all limitations, the universe produced beings capable of asking the right questions, even when answers remain incomplete. We are not the goal of the cosmos, but we may be one of its rare experiments. Matter. Learning to wonder what it is and where it came from. The universe does not explain itself. It does not pause for understanding. It does not slow down so we can keep up. Most of it remains silent, invisible, unreachable. And yet, here we are, trying to understand something that never promised to be understood. This alone is remarkable. In a reality where 95% of existence cannot be seen, meaning cannot come from certainty. It comes from effort, from the decision to keep asking questions, even when answers are incomplete, even when the universe refuses to cooperate. For a long time, humanity believed meaning required centrality, that we had to be important in the cosmic story for our existence to matter. But science has taught us the opposite. We are not central. We are not large. We are not permanent. And yet, we are capable of measuring galaxies billions of light years away, capable of inferring invisible matter through gravity, capable of discovering that most of reality lies beyond perception. Meaning does not come from dominance over the universe. It comes from engagement with it. James Webb did not reveal the entire cosmos. It revealed how much remains unknown, and that may be its greatest gift, because a fully understood universe would be a closed one, static, finished. A universe with mysteries is alive. It invites exploration. It rewards curiosity. It humbles arrogance. The fact that we only see 5% of reality does not diminish our place in the cosmos. It defines it. We are explorers, operating at the edge of the visible, interpreting shadows, listening to echoes, trying to understand a structure far larger than we were ever meant to perceive. And perhaps that is the point. Not to conquer the universe, not to fully decode it, but to participate in it, to be brief flashes of awareness inside a vast, mostly unseen reality. Matter that learned to look outward and inward. The universe may never fully reveal itself, but as long as there are minds willing to ask questions, it doesn't need to, because meaning is not something the universe gives us. It is something we create by choosing to understand what little we are allowed to see.